Very short introduction to the update of Nebula. This is a newly released work, still in the draft. Yeah, so Nebula is Nebula focused on the JKVM front end part, and it consists of two parts. That will be two very important components of JKVM. One is the random access memory, or the memory consistency check in the JKVM circuit. That is the first part of Nebula, which is called the efficient read and write memory. And the second part is about how to implement the so-called non-uniform incremental incrementally verifiable computation. So that will be the second part of Nebula, which it uses switchboard circuits. So Nebula and every component is based on folding schemes. So as I said, Nebula is focused on the JKVM front end, and the first part is efficient read-write memory in MVC. The main technique used in Nebula is offline memory checking techniques. So it was first introduced into the zero-knowledge proof by the work called SPICE, but its original technique was introduced in the 1990s. But however, I won't cover this part. If you are interested, please refer to SPICE or the section 4 of Nebula. This is the link of Nebula. Yeah, it's a newly released paper by Aran and Sally. And in this deck, I will cover the non-uniform MVC and Nebula achieves the non-uniform MVC, which is called NIVC, through the approach of designing a universal circuit, which is called the switchboard circuit. So the pain points of designing JKVM circuits is that there are many types of opcodes. So if, for example, if you have read the RISC-V cards, there will be like 50 to 60 types of opcode in the ISA. So one of the problems is how to design a universal circuit that includes all of every kind of opcode, but with higher efficiency. So in the folding, in the folding scheme, the prover and the verifier only pays for especially for the prover, it only pays for those opcodes which is actually called instead of all the opcodes. So for example, let's take RSS for example, in the RSS, every constraint every constraint is expressed by three matrix A, B, and C. So we take matrix A, for example, and every opcode is a set of constraints. So for example, A1 is one opcode, and A2 is another opcode. So there are many opcodes. And so the Nebula first construct a universal circuit by putting all different, each kind of opcode into one big matrix. So it just ran like to put A1 here and A2 here, and everyone and each opcode in this way, and everything everywhere else is put like 0. So that will be the universal switchboard circuit. The universal circuit is a matrix, but also witness of each opcode is also connected together into one large vector. And besides putting all the structure of the original opcode, Nebula also introduced some variables and constraints to construct the universal switchboard circuit. So if you refer to the section 5 of this, it should be section 5 of this paper, it first introduced one plus the number of public I/O variables, new variables into the circuit, and then we should start from the selectors of each opcode. So for each opcode, it's added one. It has one selector, indicating whether this opcode is enabled or not. If it is enabled, it will be set as 1. If not, it will be set as 0. So in this example, there are two opcodes, and opcode 2 is enabled, so its selector variable is set to 1. And and X is the public input and output. Let's suppose that each opcode has the same length of input and output. So Nebula adds the first constraint, which is everyone's selector. The sum of everyone's selector equal to 1. That means you need to select exactly one opcode in each step. And it also and then it introduces 2. L is the number of opcodes here. So there are 2 opcodes. So it introduced 2 constraints, which is it's a binary constraint, which means you have to select one or not select one. So the constraint 1 and the constraint set 2 means that the prover has to select exactly one opcode. And then the Nebula introduced some other in this example, it will be 2 minus the number of input and output constraints into the matrix. And so let's look at each opcode. So in each opcode, the constraint looks like this. So it means that the selector and the witness of that opcode, and the product of the selector and the witness of that opcode must equal to the public input and output. So that's like a copy constraint for the public input and output. So here in this variable must be equal to this variable if and only if the opcode 2 is selected. Any question here? So yeah, so that's the 3 kind of constraints added in the Nebula's switchboard universal circuit. And and all of the blue box here are some sparse matrix, and everywhere else equal to 0. So for example, here and here, and these places are all 0. So that will still be a very sparse, a large Warm CS, and you can use like Spartan or Quartz to check the correctness and make it into a snark. And yeah, so the benefit of this structure is that during the folding, you can have if some opcode is not called, the witness part and even the if you know folding, if you know there will be W and E accumulated in the instance, and all of the not touched opcode in this instance will kept 0 for the whole time. So if you, for example, in this example, you only called opcode 2. So only the area of opcode 2 is non-zero, and the IO. And for any other opcodes, it's 0. So the commitment to 0 will be for free during the folding schemes folding scheme proving process. And that's the benefit of the Nebula. So to wrap up, Nebula achieves a very cheap folding scheme and achieves the non-uniform IVC, and still and in a very simple way. Yeah. I think that will be a very short sharing, and that's all.
What does the switch mean?
Switch is like a kaiwan. It's you enable this one or enable this one. Switch is like you switch on or off.
Oh, so that's the S1 and S2.
Yes. That's the switch or selector. Yes.
And it's at the bottom or the constraint or A1 into.
Yeah, it was at the first column here. So each column is a variable, right? So this column is this column is the switch variable for opcode 1, and this is for opcode 2. And another iteration is that for Z1, if Z has this 0 area, the result of this Z1 is also like a vector, this area which is 0. So when you do the automatic products, it's still the result of which is still has this empty area. So they are all zeros. Yeah, I think my bonus talk is that's it. Yeah.
What's the red dot means?
Red dot is there are only two constraints. The red dot is the non-zero one. So everything else is 0. There are only like 1 and 2 zeros are. Yeah. Only one element is non-zero in one line, in one row. So if you are interested in the updated version, please refer to this paper.
So I forgot about the definition of the non-uniform IVC. What does it mean?
It means that in the IVC, each step is same. If you have f applied like n times, but in the non-uniform IVC, you have several kind of function f. Have f1 and until fl. Yeah, in each step you can incur different kind of operation. I think I'm making some time for it to get some seats downstairs. Yeah.
Yeah, so sweet. So the non-uniform here is means the OP course, the OP course is
Yes.